All right, so here is our free body diagram PowerPoint. So what I would suggest right now is you pause this and get a piece of paper to take some notes. We're going to do a reading and some other activities, but this is our first introduction to free body diagrams. So here is what a typical free body diagrams will look like. And we're going to go through some examples. All right, so we can't talk about free body diagrams without talking and learning about forces. So here we have a force. I'm not going to have that pointer. So here we go. A force is caused by an object to change its velocity, which just means that it's changing either its speed or its direction. Remember what velocity is from last week? It's a change in speed or direction. Force is also a vector quantity, which means that it has a number attached to it, which we call magnitude, and it also has a direction. So we're going to use arrows to represent forces here with a force vector. You can see that there is contact forces between objects that touch, and there are field forces between objects that do not touch. So just because something is not being touched does not mean that there is not a force being applied to it. So just keep that in mind. Right, so this slide here has an SI unit for force is the Newton. So we're going to be learning a lot about Newtons. SI just means that that is the standard science instrument that we use. So when we're talking about forces, we're going to be using a Newton, which is a kilogram times meters per second square. So this kilograms times meters per second square is what we call a Newton. All right, so this table here has all of the different, or most of the different forces that we're going to be using. This is a really good table. You might want to pause and write some of this down. A frictional force, we use a symbol with an F and either a subscript of another F or FRI. This is a force that is between a surface and an object. And it's always opposite some sort of pulling force or applied force, and we'll talk more about that as we go through some examples. Tension is another type of force, and that is represented with an F and then a lowercase t, which is a subscript. That just means that the force is transmitted through a string, a rope, a wire, something that can cause tension, which has to be a string, a rope, or a wire. Normal force is F with a subscript of an N usually, sometimes NORM, but usually just an N. This is the force where it's opposite of gravity. So normal force is exerted on an object when it's on top of another object. And we're going to go through some examples, but like something resting on a table is a good example of a normal force. Air resistance, or FA, is a force exerted on an object that usually is traveling through air. And we're going to talk a lot about that when we're looking at gravity or free falling. Applied force is when it's being a push or a pull. Spring force is when we have a stretchy object that's usually a spring. We don't really have very many examples about this. And then the FG is gravitational force, and that is anything that it's experienced gravity because of Earth, which is most things because we are on Earth. All right, so free body diagrams are used to show relative magnitude and direction. So that means we're going to have an arrow showing a certain direction, and we're going to have a number that is the amount of force, the Newton, so the number part of that equation. So these are the steps that you're going to kind of go through to draw a free body diagram. So that you're going to draw the object as a box. The larger the force is a longer arrow. The direction of the arrow should show the direction that the force is acting, which isn't always, can be a little bit confusing depending on what type of force it is. Always label your forces so we know what we are looking at, what type of force is acting on it. And then this last part is just about with constant velocity vectors are equal and acceleration or deceleration vectors are unequal. So if something is speeding up or slowing down, the arrows should be uneven. If something is not moving or at a constant speed, those arrows are going to be the same length. And we'll have a chance to practice that. All right, so here's an example. This free body diagram is It could be lots of different examples, but here we have an example of a book on a table being pushed to the right at a constant velocity. So that means the velocity is not changing. So you can see that the arrows are all equal to each other because there are equal forces acting on it in all different directions. Here we have the force of gravity pulling it down. We have the normal force acting up. So the table is acting up just as much as gravity is pulling it down. Now this book is being moved, but the applied force is equal to the friction force, which means it's moving at a constant speed. Here we have an example of a parachutist jumping out of an airplane. So here we have the force of gravity is equal to the force of air resistance. You can see these arrows are the same length or magnitude. That just means that it's falling at a constant rate. It's not speeding up, it's not slowing down, it's going the same speed. All right, here we're going to get to some examples. So I would suggest right now that you try and do this before we go to the next slide. So here we have a grocery bag that's resting on a table, and you can see that there's nothing pushing or pulling. There's no other forces besides the force of gravity acting upon this bag. So take a minute, you can pause this. Where are all the forces, and draw a force diagram. All right, so this is what your force diagram should look like. Again, we have the force of the table, or the normal force, is acting up. The force of gravity is acting down. It is not moving up or down, so those magnitudes or those arrows should be the same length. Here's another situation. We have a car, or sorry, not a car. We have a cart that's being pulled by a sleigh. So the horse is pulling this sleigh here. And you can see that there are some frictional forces acting on it. There's also gravity and the normal force. But it is moving, it is speeding up as it goes along. This horse is pulling it. So here we have the force of Earth, or the normal force. We have gravity pulling it down. But then we have friction, and we have the horse pulling. So the applied force of that horse is pulling it. So you should have arrows going in all different directions. All right, so here's a typical free body diagram. We usually have normal and gravity, and some sort of applied and some sort of a friction if it's going side to side. The next thing that we're going to do together is going to be kind of introducing forces and practicing this quite a bit.